In this episode, we're going to model a magnetic paddle shifter for sim racing in Fusion 360. The particularity of this shifter is that it will use ball bearings for super smooth action. I will describe in details all the steps I used to model this shifter from scratch. I will also include the assembly of all the mechanical parts. At the end of the episode, you should be able to design, model, and 3D print your own shifters easily. Let's get building. My first step here in Fusion is to create a new component. We will call this component Base. I then create our first sketch to define the main profile of the shifter's base. I start by creating a rough outline, starting with this horizontal line, then a vertical line that connects to it. For now, the dimensions don't need to be precise, those will be set up in the next stage. I then create a construction line to position the ball bearing center. I now create a circular shape from this center, around which the lever of the shifter will rotate. I then proceed with the rest of the profile outline, with another vertical line, and then another horizontal line that will mark the location where the lever will rest. I continue to build the profile with one more vertical line, and another horizontal line. And finally, we can connect the last line to the circular shape to close the profile. We can now start to dimension the profile to match our design intentions. If some of those measurements seem very specific, it is because I am basing those measurements on existing shifters I have built in the past. The base of the shifter will be 30 millimeters long. This suddenly increases the size of our circular shape. I reduce its diameter to go back to a more sensible shape. I then change the diameter of the circular shape to 12 millimeters, as the ball bearings we will be using have an 8 millimeters diameter. I then dimension the base arm to be 21 millimeters long, and the top to be 26 millimeters. As for the arm itself, it will be around 4.816 millimeters. I then set the height of the center of the ball bearing to be 18.6 millimeters. And finally, the base of the shifter to the bottom of the arm is going to be 25.18 millimeters. I then switch the solid circle to a construction circle and proceed to use a 3-point centered arc to close the profile. At this step, I use some fillet to either reinforce the structure of the part or just smooth the overall shape of the base. In this corner, I use a 10 millimeters fillet that will provide strength. And in this corner, I use a 35.25 millimeters fillet to soften the shape of the part. And here we have our first profile completed, with measurements that we can come back and tweak later on if we need to. Now, let's extrude this profile to create the main part of the base. Let's make it 30 millimeters wide. In the next few steps, we will carve this first part by removing material, just like a real machining process would. I will start by machining the back of the base, so I create a sketch aligned with the back face. Using two construction lines on each side, I define the thickness of the base plate and the thickness of the side walls. I'm using 4 millimeters thickness on the bottom and on the sides. I then create a horizontal line for the bottom and two vertical lines for the sides. Again, I do not worry about the dimensions here. We will use constraints to define those. One final line is used to close the shape. Using a horizontal constraint, we can square the shape. And finally, we just need to conform this line to one of the points at the top of the base. We can now finish our sketch and extrude our profile. We use the cut option with a 27 millimeters depth to machine the part. Let's continue to refine our part. We will now carve the space where the lever will be able to travel. I create a sketch on this plane of the base. I then project the bottom of the base arm to our sketch. This will be the resting position of the lever. I then use a construction line to define the opening on the base. The higher this number, the smaller the lever will be able to travel. Here, I will use a value of 11.6 millimeters. I then close the profile with a horizontal line. We now have a profile we can extrude to cut into the base. I'm using the To Object option to confirm the cut to the length of the base's arm. We can see that our part is progressing nicely. We will now create the slots that will hold the ball bearings on each side of the base and the holes that will allow the shaft of the lever to rotate freely. I create a sketch on one of the sides of the base. I then project the arc of the base to mark the center of the ball bearings. The ball bearings I am using have a diameter of 8 millimeters. I make the openings 8.5 millimeters, so we have additional clearance once the part has been 3D printed. The shaft of the lever will be 4 millimeters in diameter. So, here, we can create another circle of 6 millimeters diameter. This will allow the shaft to go pass through, but will prevent the ball bearings from moving with it. The first hole is 3 millimeters deep, as this is the width of the ball bearings I am using. Instead of cutting directly into the base, I will create some temporary bodies that I can then mirror to carve both sides of the base. For the center hole, we want to extrude all the way through the side. So, once again, I use the To Object option. And, again, I create a new body. We can now merge those two bodies into a single compound part using the combine operation. I then create a center plane between the planes on each side of the base. I can now simply mirror our temporary part around that center plane. We now have two perfectly aligned temporary parts we can use to carve the base. In this simple step, we will create another opening, this time for the magnet. I create a sketch and select the related face of the base. I rotate the sketch in the orientation I prefer. I create a construction line at the center of the base. I then dimension the offset to the tip of the base to the center of the magnet to be 8.5 millimeters. The magnets we are using are 10 millimeters in diameter. So, once again, I will create a circle that is slightly oversized to accommodate for the 3D printing inaccuracy. Finally, we cut this profile in the base with the usual operation. We will now refine the shape of the base to make it look a bit more pleasing. Once again, I create a sketch on the top of the base. I reorient the sketch. I create a construction line in the center of the base. I already have an idea of the shape I want. For this, I just need to create some simple lines and fillets. I start with a line at the top, another line at the center, and finally, a diagonal line to connect them. Now I can simply play with the diagonal line to see which shape I like the most. I then use fillets to smooth the profile. And because we already have an opening for the magnet, I can easily see how much material I can remove. I can continue to move points around to refine the profile even more. I can also use specific dimensions to constrain the profile. Once I am satisfied with the profile, I can mirror it around the construction line. I then extrude the two parts of the profile to carve the base. I make sure to use an offset during the extrusion to carve all the way through the base. A few more steps, and we are done with the base. Let's now create the openings for the switch. I am using Cherry DC2 switches with a 9.5 mm hole spacing. I create a sketch on the front face of the base. I project the top edge of the base to the sketch. I then create a construction line in the middle of the face, and then another construction line to space the holes. We will set this one to 9.5 millimeters divided by 2 to match our switch. I want to create an opening that will be high enough so we can tweak the position of the switch up and down easily. I create 2 construction lines to specify the top and bottom of this opening. I then create 2 circles with a diameter of 2.2 millimeters to allow our M2 bolts to fit easily. I then connect those 2 circles with 2 vertical lines. I don't need to align those precisely. We can just use tangent constraints on both lines to align them to the 2 circles. Once this is done, we have a nice parametric opening for the switch. I can change the position and the height of the hole. I want the position of the opening to be precisely defined. So, I create a construction line from the projected top edge to the top of the hole. This dimension will be 4.1 millimeters. I am now happy with the opening. I can use the mirroring function to create the opening on the right. I select the 2 circles and the 2 lines and mirror them around the center line. We can now extrude those faces to cut the openings in the base. We can now create the holes that will allow us to fasten the base to the hub of our wheel. Again, I start by creating a sketch aligned with the relevant face. I add a construction line to mark the center of the face. I then create another construction line to mark the offset of the first hole. I create a circle of 4.4 millimeters diameter to allow for M4 bolts to be used to secure the shifter's base to the wheel. I use another construction line to define the size of the hole. I will create slightly elongated holes here, so we have some wiggle room to attach the shifters to the wheel. As we did before for the switch openings, I once again create 2 parallel lines to connect the 2 circles. And I use the tangent constraint to create perfectly shaped holes. I will now proceed exactly the same for the second hole. I could also use a mirror or a copy of the profile if I wanted to. I can now dimension the spacing between the circles. 1.5 millimeters seems like a good enough margin here. Finally, I offset the holes on the base. The opening on the left seems a bit off-center, but it is set up this way to account for the lever and the fact that I want to be able to install the shifter through the lever, as we will see later on. Finally, I select the relevant faces and extrude the openings through the base plate. We will now create channels for the switch wires to be able to run inside the base plate of the shifter. We create a new sketch at the base of the shifter. I create a construction line to define the offset of the channel. I then create a line to define the channel direction. This first segment will be around 17 millimeters. I then use an arc to connect this line to the other side of the base plate. I now offset the arc and the line to define the wire channel width. 3.5 millimeters should be plenty to run our wire. I create a construction line to mark the center of the plate. I then close the center arc with another smaller arc. I use a tangent constraint to make sure the curvature of the channel is smooth. Finally, to ensure that the mirrored lines will flow properly, I create a vertical construction line. I will then use this line to make sure the smaller arc is tangent to this vertical line. I then mirror the channel around the center line. We can now finish the sketch and extrude this new profile with a depth of 2 millimeters. We now have perfectly smooth channels to hide our wires. It is now time to smooth a bit our part using some nice fillets. First, I select the outer edges of the base. And then, I use a 1 millimeter fillet to smooth them out. I will also select all the inner edges of the wire channels to ensure there is no risk of cutting our wires. I use a 0.6 millimeters fillet. Our base part is complete and ready to be printed. We can now design our second part, the lever. I start by creating a new component called, you guessed it, lever. This will activate the lever component as our working component. Then, I create our first sketch for this component. It will be aligned to the interface of the base part. I set up a construction line to define the length of the lever, and then a second construction line to determine the top part of the lever. Using a coincident constraint, I snap this line to the arm of the base. I then define the actual profile for the lever, starting with the top horizontal line, then the thickness, and another horizontal line for the bottom. I then project the base opening for the ball bearing onto the sketch. This will be the rotating axis of the lever. For the thickness of the lever on this side, I use a 12 millimeters diameter, so it matches nicely the base shape. I can now dimension the construction lines and the profile, starting with the length of the lever at 35 millimeters. Then the top line at 30 millimeters. Using an equal constraint, I can conform the bottom line to be the exact same dimensions. I can now create a construction line between the two profile lines. I will use the center of this line to create a construction line that will connect with the center of the ball bearing. I just need to create two additional lines to connect the arm of the lever to the rotating axis profile. I can then use parallel constraints to conform those lines. This has affected the thickness of the lever, as this one is not set up yet. So, we proceed to set this one up with a thickness of 6 millimeters. That should be plenty strong once printed. I then fillet the lever lines to create a more pleasing shape. I then trim the circle of the lever axis, so I can fillet the connection of the lever arm and the lever axis to a nice 9 millimeters. Finally, I create a circle with a 4.2 millimeters diameter. This will be the opening for the 4 millimeters shaft. Our lever profile is now complete. We can finish the sketch and extrude it to its final dimension. The lever width will be 21 millimeters. We can now visualize what the final shifter shape will look like. Because we created the lever directly aligned to the inner base face, we need to offset it slightly. We take some measurements and we see that the gap between the lever and the other face of the base is 1 millimeter. So, we simply use the move operation with an offset of 0.5 millimeters. And we end up with a perfectly centered part. We can now proceed to create the opening for the magnet that will be attached to the lever. We create a sketch on the top face of the lever. We then simply project the opening from the base to the lever. This will ensure a perfect alignment of the magnets once we actually build the shifter. Once this is done, we can use this profile to create the hole in the lever using a simple extrusion. Here, I use a double-side extrusion to make sure to cut the lever with the proper depth. We can now add two openings on the tip of the lever where we will attach the paddle. I create another sketch on the top face of the lever. I start by creating a centered construction line on the lever face. I then create a perpendicular construction line that will determine the offset of the holes. The offset between the two holes will be 10 millimeters, so I set a half offset of 5 millimeters here. I then add another dimension to define a 6 millimeters offset to the tip of the lever. We will use M3 bolts, so the opening will be 3.2 millimeters. As we did before for previous holes, we create a construction line to define the length of the opening. And we then proceed with another circle and two parallel lines to close the profile. And, once again, using tangent constraints to finish the profile. I first set the offset between the two circles to 4 mm, but then decides on a 2 mm gap. It's now just a matter of mirroring those segments using the center line. I feel like the holes are a bit small, so I finally settle on a 3 mm spacing. I select the faces and extrude the profiles to carve the holes in the lever. We are pretty much done with this part. Because the lever will be held with a shaft through 2 ball bearings, it will not be very practical to attach and remove the lever repeatedly. Therefore, I decide to create some openings in the lever, so we can easily attach and remove the whole shifter without having to disassemble it. The lever will still be plenty strong, even with those additional holes. I activate the lever component. And then, I create a sketch aligned with the bottom of the base. And I simply extrude the 2 holes from the base to cut through the lever itself. This opening should be big enough to fit an Allen wrench. The lever is now complete and ready to be printed too. Just to be on the safe side, I decide to use the section analysis tool to visualize the space between those new holes and the shaft opening on the lever. There is no problem, and the gap is large enough, so I don't need to offset the holes. The 2 main parts of our shifter are done. In this final section of the design, we will import the mechanical parts that are missing to validate that there are no clearance issues or dimension problems. This will allow us to preview exactly what the full assembly will look like. Over time, I have built a collection of parts for that exact purpose. We will start by importing the ball bearings I am using for this build. 8 mm diameter, with a 4 mm hole and 3 mm width. Once imported, I eyeball the alignment of the new component. As this is just a final check, it does not need to be very accurate. I then copy and paste the ball bearing and move the copy into position. We can now insert the shaft and circlips assembly. Once again, I will rotate and roughly align this component to the ball bearing center. I offset the shaft, so the slot for the circlip is flush with the ball bearing. I then find the circlip body in the component, and I move it to the proper location to be flush with the ball bearing. We can see here that if we measure the shaft, it is 50 mm long. However, our shifter base is 30 mm wide, which means the shaft we need to use here should be 35 mm to account for the circlip spacing. So, we need to shorten the shaft to match this size. I'm simply creating 2 offset planes with a 15 mm spacing between them. This will allow us to split the body of the shaft in 3 parts. I hide the other components so we can see what we are doing better. I proceed to split the body of the shaft. I then find this now useless body in the component, and I simply remove it. I then just need to move the right side of the shaft back to the left side with a 15 mm move. I combine the 2 bodies and we now have a 35 mm shaft. Using the component option in the move operation, I then bring the right circlip back into position to be flush with the right ball bearing. We can now confirm that our assembly will work perfectly with the ball bearings and the shaft. Let's add the 2 magnets. For this shifter, I will be using 10 mm diameter magnets with a height of 5.8 mm. I already created a simple part in my library for those. So, I just import it as a new component, just like we did for the other parts. Once again, I align the new component to the lever first, making sure the height is correct. I then duplicate the magnet component, and I move it up to align with the base of the shifter. It will be a little proud on the top, but I am okay with that. I can always create a cap for it if I want. As we can see, our 2 magnets fit well and are perfectly aligned. Let's confirm our setup for the switch is good by importing the corresponding part. I am using Cherry DC2 switches. I will import the component from my electronics parts library. For those complex parts, I usually get them from Trace Parts, either from Fusion directly or through their website, where you can download countless types of parts. Once imported, I just proceed to align the part as usual, first rotating it to the correct orientation, then aligning the holes of the switch to the openings on the shifter's base. As we can see here, those will be perfectly aligned. I'm also making sure the actual switch is aligned with the top of the base edge. Finally, I move the switch so it is flush with the shifter. The clearance and alignment with the wire channels seem to be perfect. We can now import a paddle and its mounting bolts. You can use various shapes of paddles depending on your preferences. I will not model specific paddles in this video. You can find many different references and shapes online. I will just import from my library some reference paddles I've been using in the past. Those paddles use M3 bolts. After importing the component, I proceed to align it with the shifter's lever. Once again, the clearance and alignment with the holes is great. We are almost done. As a final step, I will import the M4 bolts and nuts that we will use to secure the shifter to the steering wheel's hub. Again, I will use existing components from my library. Once imported, I once again align and offset the component to match our openings. The bolt is obviously a bit long. I need to shorten it a bit. I find the nut in the assembly and move it up. Then I will use the split body function and the base of the nut to cut the bolt flush with the nut. I just have to remove the extra body now. Everything seems fine. I proceed to duplicate the bolt and offset it by 10 millimeters. We now have a full assembly with all the different parts and fasteners, and we can use it to confirm that we are happy with our design. Upon final inspection, I realized that the lever openings to access the mounting bolts are probably a bit too narrow. I feel it will be better if the two holes are actually one single opening. This is very easy to correct. I first activate the lever component. Then, I isolate that component so we can see better what we are doing. I then create one final sketch on the top face of the lever, the one that is parallel to the base. Now, I simply project the segments that are in between the two holes. I then connect those projected segments with two lines. And I use tangent constraints to align those lines with the two holes. The final step is a simple extrusion to remove the gap between the two holes. We end up with a single wider opening, which will be much more practical. And this is it. Our magnetic ball bearing shifters are done and ready for print. Thank you for watching. Don't forget to like and subscribe to this channel if you want to get notified when I upload new videos in this sim racing series. Make sure to check the video linked in the description if you want to see how to print and build those shifters. Happy building and happy racing!